So we have established now that as long as the sequence that we're dealing with is delta k constant, which you can look at that two ways, that would mean that the kth differences are constant, or you could look at it as the kth derivative is constant. That means the same thing. Unfortunately, we're not going to be able to take derivatives because we're given a data set, not a function. If you have a function, you can take a derivative just like we did up here, but the only way to look at a sequence is to actually compute those differences just like we did in red and then in red and purple over here. So as long as we have a sequence that is delta k constant, then we can fit a degree k polynomial to that data. Let's take a look at how we're going to do this. Well, there are algebraic ways to do polynomial fitting. It does get pretty exhaustive because it usually results in a system of equations that needs to be solved, and then now you have a whole new algebraic problem to deal with. So we're going to actually take a look at doing this with technology because it's readily available and it's much more efficient. So we'll take a look at a couple of examples here, one which will not give us much context, and then we'll look at a contextual example which polynomial fitting will make a lot easier to solve. And I think it's a really cool problem that we'll look at next. So first of all, which of the following sequences are delta k constant for some value of k? Where applicable, use technology to find a polynomial of order k that solves the sequence. So I'll show you how to use technology to solve this. All right, let's take a look at the first example. So I'm just going to start off with, I'm going to write it over here. And 2, 3, 7. You can write it down a column if you want, like we did in our table above, but I'll just look at the differences here. So the difference between 2 and 3 is 1. From 3 to 7, that's 4. Then 7, and that's an increase of 10, and that's an increase of 13. Now, right now, this is the first difference, and the first differences aren't constant, so it's not a delta 1 function. In other words, this data is not linear. As you can see, the rate of change is changing, and it's getting bigger and bigger. Now, if I look at the second differences, there's an increase of 3 in the rate of change, 3, 3, and 3, and look at that. The second differences are constant, and therefore, this data right here is delta 2 constant. What does that mean? Well, that means we can come up with a function to model this sequence of the form y equals a2x squared plus a1x to the first plus a0. Again, you could write this as a0 x to the 0 if you want to have that there. That's not really necessary. What we need to know is what are these values here? What are a2, a1, and a0? a0, by the way, will just be your starting value, assuming that happens, that we associate this value, these are kind of like our y values here, and then our x values, typically we start at 0, 1, 2, 3, 4, and 5. Does it have to be done that way? No, it just makes it convenient to start your initial term being x equals 0. We've kind of done that. We've called our initial term a0 or x0. So let's go ahead and see how we can do this in Desmos. Okay, so here in Desmos, the first thing we want to do is actually enter our data in. As you can see, I've already done that, but let me show you how I did that. So we're going to clear this out, and we would first click on the Add Item button so that we can put in a table. By default, your very first table, your x and y values will be labeled x1 and y1. You don't want to relabel these as x and y because x and y are system variables, and that will try to generate something over here in the plot. If you use the subscripting like it shows here, then these are actually assumed to just be data sets. So because we typically start our value at a0 or x0, whatever you want to call it, we would start here at 0, and as you can see, after you enter in 0, 1, it's going to auto put in the value for you. So we have 6 total points, 2, 3, 4, 2, 3 are our values. 2, 3, 7, 14, 24, and 37. Okay, now to actually get this window, normally you're going to be from negative 10 to 10 on the x-axis. And so in order to see that data, click on the little wrench, and we'll set x to go from, we'll say, 0 to 6, since that's just a little more than our x values go to, and we'll set y to go from, say, 0 to 40. And all I'm trying to do here is just visualize the data so I can see that this data is in fact quadratic. I'm going to zoom out a little bit, and you can see that that looks parabolic. It doesn't always mean that it's perfectly parabolic, but we've already checked the second differences, and we know that based upon that we have a delta 2 constant function. So now in order to do the regression, we are now going to reference x1 and y1. And so we're going to actually sort of write an equation that's going to be of the form y equals something x squared plus something x plus something. And we want to reference y1, so we'll say y1, and you can see it references the 6-element list. Now, if you press equals, that's not going to do what you want. You actually want the little tilde, the little wiggle right here. And now you don't have to do a2 x squared, x1 squared. You could just do a x1, and now caret 2. Okay, so you have to do x1 squared. And you can already see that we get an estimate of the best fitting polynomial. This is called a regression analysis. And you can see here that it says, okay, for this black quadratic function, a should be about 1.5. Now you can see it's not a perfect fit. It doesn't go through all the points, and therefore it doesn't model our sequence perfectly. This value of r squared, the closer this thing is to 1, the better our fit is. If it's exactly equal to 1, then we have a perfect fit. Now we need the other terms, so let's do plus, we'll just say bx1, and okay, let me take that power out of there. Now we're a little bit better, 0.9948, but you can see it's still not a perfect fit. We're still missing the initial point, and that's because our y-intercept is not there, so we'll say plus c. Now I'm just using a, b, and c, so I don't have to type a2, a1, and a0, but as long as you're not using x and y, you can use any letters here you want. And you can see now we have an r squared of 1, and it tells us that a is 1.5, b is negative 0.5, c is 2. So let's come back over here. And what we've just found, and I probably want to call, we can call it terms of the sequence whatever we want. We'll just say x, these are y values. So we would have y equals 1.5 x squared minus 0.5x plus 2. Typically, the way we would write this as a solution to a sequence, we might call this a0, a1, a2, a3, a4, a5, and instead of using x and y, we may use n. So the way we would like to see this usually is these are our values of n, and these are the values of an. So alternatively, we might write an equals 1.5n squared minus 0.5n plus 2. That way it looks more sequence-like. For the second one, let's check those differences. Again, I'll just go ahead and write those values down here. So we have 1, 8, 27, 64, 125, and 216. Differences here are going to be 7. Here we have a difference of 19. We can see we're not going to have constant first differences. Here we would have, let's see, 37, I believe. And then here we would have 61. Here we would have, okay, let me make sure, I know I'm going to make a mistake if I try to do mental math on video here, so let me just subtract these. That's 91. Okay, so we don't have constant first differences. If we looked at the second differences now, we would have a difference of 7 to 19 is a difference of 12. 19 to 37 is a difference of, let me just do this, 37 minus 19 is 18. 61 minus 37 is 24. So we don't have constant second differences either, and a difference of 30. And now if we take the third differences, okay, now we're moving on to thinking this could be cubic. This would be 6, 6, 6, and we do have constant third differences. So what we're going to be looking for, and I'm just going to go ahead and use the n and an notation, we would have something of the form an equals a3n cubed plus a2n squared plus a1n to the first plus a0. So that's the cubic, the quadratic, the linear, and the constant terms. And so now we have to dump this data into our technology to compute that regression output for us. So I'll go ahead and enter that table in. We have 1, 8, 27. So all I'm going to do here is just delete this 1, 8, 27, 64, 125, and 216. Okay, so now you can see our values are really large in the y direction, so I'm probably going to go up to about 230 so I can see those data points, and there they are. So it looks quadratic, right? But even cubics kind of have a little bit of that shape. So what I'm going to enter here now is y1 tilde ax to the third. Okay, now you see I have an error right here because x may not be used as a regression parameter. Try using a list. Okay, so I have to do x1. It's a little bit tricky once you already do that. All right, there we go. ax1 cubed. Okay, you can see that doesn't fit very well, but if we start adding on x1 squared, I'll say getting a lot better here, 0.9997 plus cx1. Now you see right now we have a perfect regression fit. That's just because it's likely going to be the case that if I add a plus d, that, well, actually that, I think it probably just rounded that r squared off. But in any case, if you're going to have a delta 3 constant, you have a delta 3 constant, then you want to have 3 terms in descending powers of x, and then your constant terms. So we have 1, 3, 3, 1 as our coefficients. So this sequence will have a solution of 1n cubed plus 3n squared plus 3n plus 1. And so we found that without having to do any sort of method of iteration.